Welcome. Here, we're going to really take some time and get into the nitty-gritty of vertical throwing, both the concept of vertical throwing and some of the more complicated word problems that we've been seeing. If you still have questions on how the charts work, please reference the other video where I go through free fall charts, vertical throwing charts, and equations with free fall and vertical throwing. Here are the 3 rules of vertical throwing. I recognize that some people may have missed these, so I wanted to make sure that they were put into the presentation so we can all see them exactly as they are. The 3 rules of vertical throwing are critical to understanding how to solve a vertical throwing problem. And I just want to remind you that this is only applicable to symmetrical vertical throwing problems. We will only deal with symmetrical vertical throwing problems in this class, meaning that we will never have a situation where you throw something up and it won't come back down to the same spot where you threw it. In case you were wondering, what would asymmetrical vertical throwing look like? It would look like something like this. If you threw it up into the air, but then let's say you didn't catch it and it fell back a greater distance than it went up, and the distance up did not equal the distance down, that would be asymmetrical vertical throwing. We will never do that in this class. We will only do with symmetrical vertical throwing. So these 3 rules always apply to symmetrical vertical throwing. The time going up equals the time going down. In other words, T up equals T down. Okay? The instantaneous velocity at the top of the path is 0. We're going to get into that a little bit more, but essentially what we're saying is that every single time an object is thrown up vertically, right at the top of that path, 0 meters per second. And the speed it leaves equals the speed it returns, but opposite direction. So another way of thinking about that is V0 is going to equal the negative of the final V, because it's going to return the same speed but opposite direction. That's what the negative would mean. So a couple ways of thinking about this. Let's really try to get a little bit more into the concepts. Let's think about this situation, this picture that I absolutely love drawing, little Susie throwing a ball. As the ball goes up, once it's in the air, the only thing pulling it on is gravity. And we know that gravity is constant. And gravity is an acceleration. So if you throw something up and gravity pulls it down, that's going to cause the ball to slow down as it goes up. It hits the top of the path, and for just a brief moment in time, it goes 0 meters per second. And what happens in that exact small, brief moment in time is it changes direction. That's when it stops going up and starts coming down. So as you threw the ball up into the air, it slowed down. It then hits 0, changes direction, and speeds up as it comes back down. And it speeds up as it comes back down. Now let's think about that. You throw the ball from here, let me get a different color. As it goes up, the speed decreases till you hit to the slowest speed here. And then the speed increases as it comes back down until you hit the highest speed here. So objectively, if you look at this chart, the lower you are on the chart, the faster you're going. The higher you are on the chart, the slower you're going. Okay, what does that mean? Let's just look at this. If I have point A and I have point B, the higher up you are, the slower you're going. The lower you are, the faster you're going, because we're just talking about speeds. Yeah, I know the velocity changes, the direction changes, but this is going to become, and we're going to see this a little bit more in the next slide, these are going to be symmetrical. So the speed here at A would be equal to the speed it's going here at C. And both A and C would be faster than B. Because wherever you are, the higher up you are, the slower you're going. So D would be slower than all three of the previous dots. And E would be the slowest. So let's think about it. As it goes up, it slows down. It approaches 0. And then, after it approaches 0, it becomes negative. But then it gets bigger in the negative, which is really speeding up. Conceptually, this is what vertical throwing is. Since the starting speed and the ending speed are the same, we also know that the time that it takes to go up is it'd be exactly the same as the time it takes to go down. If the times were different, then the speeds wouldn't be the same, because once it's in the air, it all experiences the acceleration of gravity, negative 9.8 meters per second squared. So let's look at that in another way. All right, let's look at that like this. And I'm going to make a drawing kind of similar to one that you saw in the physics classroom. Okay? Try to space it out a little bit. I want you to see the symmetry that exists in vertical throwing. In the physics classroom, they said round gravity to the nearest whole number. Okay? And we are going to get to a problem like this again, but I want to make sure you understand. Let's just say you threw something up plus 40 meters per second. And gravity, rounded to the nearest whole number, would be 10, negative 10. So then the speed here would be plus 30, plus 20, plus 10, 0, minus 10 meters, and all these are meters per second. I know, Mars rover. Minus 40, okay? So when I say that vertical throwing is symmetrical, at these points, when they're going the same speed, they have the same height, they have the same distance. It is a symmetrical point. Whenever it passes that point, either going up or down, it's going to be going the same speed. The only difference is that one is up and one is down. Here, they're passing the same point, so they're going the same speed. The same point, the same speed. So essentially it's symmetrical. You have all the positive speeds going up on one side, and it's going to be the exact, like almost as if you put a mirror right down the middle. All the speeds kind of get reflected over, and instead of going up, now they're going down. This is the symmetry that I want us to see. And if the speeds are the same, then the displacements are the same. So back when we were doing the charts in the other video, when the speeds were symmetrical, that meaning it would go like 19.6, 9.8, 0. Here, just do a quick one. We had a quick little chart. I'm just going to do a super quick little chart right here. 0, and the initial velocity was 19.6. And then we had 9.8 at 1 second. And then at 2 seconds, it was 0. And if you don't remember this, go look at this video. 9.8. And then negative 19.6. And I said in that video, the displacement here and the displacement here would be the same. Why? Let's look at the picture. When the speeds are the same, they correspond to the same height. I know these are different numbers, but as long as the speeds are the same, they correspond to the same height. So that means these two displacements should be the same. This would be a unique displacement because there's no, I'm going to put unique rather than unique displacement rather than a symmetrical one, because there's only, if you look at the top, when it's going 0, there's no other part of the mirror in terms of the picture. There's nothing to reflect it. It's only going 0 that one brief moment. So yeah, vertical throwing is symmetric. So let's get back to that physics classroom. Let's really try to think about this. If a ball was thrown at plus 40, fill in the speeds in the following picture. Actually, we just did that. I put it on the early slide, but that's okay. You might remember the physics classroom problem said like A, B, C, D, E, F, G, H, I. And it said, okay, if the ball's thrown up plus 40, right? And then it said, what letter would it be, say, going downward 20? And then you could kind of count it out. But I'm going to ask a slightly different question. What letters, and we're still rounding to the nearest whole number, what letters is it moving, I'll say 10 meters per second. And because I say 10, I'm not talking positive or negative. I'm just talking about a speed. So let's think about this. There's going to be 2 correct answers. Here it's going up 40. Then it's going to be going up 30, 20. D is 10, E is 0, F is negative 10, G is negative 20. It's the same picture as the other slide, guys. I know my handwriting is getting a little worse, but negative 30, negative 40. So I want to know what 2 letters is it moving 10. I don't care when I don't have a sign. We don't assume it's positive. We assume we don't know the sign. So we assume all of these are positive. This is why I like to put the positives in front, because the positive means that's going up. D and F. It's symmetric. That's kind of what it was trying to get at when you were doing the physics classroom. So if you saw that this was 10, you wouldn't need to count over to F. You could just see, oh, the one in the same line is going to be going the same speed. So C and G would be the same speed. B and H would be the same speed. A and I would be the same speed. Hey, and isn't that one of the rules of vertical throwing? The speed it leaves is the speed it returns, but opposite direction, because it's symmetrical. Now, these were the questions that nobody liked. These were the questions that had the little speedometers. Okay, and rather than putting in the speedometer here, I just kind of put it all into words. This is essentially the exact same question that we saw in physics classroom, but in words. I just kind of want to go over it one more time, make sure we're all on the same page with it. If a ball was moving 30 meters per second upward, plus 30, okay, after being in the air for 2 seconds, I'm going to make my little chart. Making my chart. Oh, at 2 seconds, I'm going to put plus 30. Okay, making my chart. And it's going to keep going. I'm going to stop for now. I don't know how long it goes, but let's go see what I'm looking for. At what time would the ball be moving downward 20 meters per second? A lot of people did not necessarily read the question fully in the physics classroom, and they would miss the keywords like downward, and they wouldn't know it would be negative 20. So we want to find at what second it's going negative 20. And again, we're still rounding to the nearest whole number. So we want to get this chart to say negative 20. For those of you who are completionists, you can go back if you want. If you really want to do that, you can go back and you can realize, oh, okay. All right, so initial velocity is plus 50. Okay, that's good. How did I know to go back? Because we know that the acceleration is negative 9.8. Rounded to the nearest whole number is 10. So when you go backwards to the chart, you do the opposite sign. When you go forwards in the chart, you just minus 10. minus 10, minus 10, minus 10. I could keep going. Wait, Pizzuto, how long does this chart go to? Well, if you threw it at positive 50, where are we going to stop? You know what? Let's find out. We got to stop at negative 50. That's how you know when the chart is over. Because the speed it leaves is the speed it returns, but opposite direction. And getting back to the actual question, I want to know what time the ball is going negative 20. 7 seconds. Okay? And don't forget the symmetry here. What's the other time it's going 20 meters per second? The other time it has a speed of 20 is 3. But the difference between 3 and 7 is that 3 is going up, 7's coming down. What are we going to know about 3 and 7? They would both have the same displacement. If we were filling in a displacement, if we threw a displacement on this chart, and we could, we're not going to, but if we wanted to, we would know that these two would have the same displacement because they have the same speed. These would have the same displacement. These would have the same displacement. We are just looking for patterns. Wait, you can add more columns to this chart? Guys, the TV chart can be flipped horizontally or vertically, and I want you to understand the connections that exist. So if you solve for these 5 displacements, if you solve for 1, 2, 3, 4, 5 displacements, you've actually solved for these 5 displacements too. Understand the concepts. So as we go through this, I'm sure that we want to see the vertical throwing equations again. I know I mentioned it in the other video, but essentially there's going to be 3 that we use. I imagine that you guys mostly may pick the first 2, and you'll stay away from the third one. But I'm going to show you that the third one actually makes your life a little easier if you don't get scared of it. If you ask me, I really like the third one. But these are the vertical throwing equations. Essentially, they're the kinematic equations with an initial velocity. And a vertical throwing would have an initial velocity. When you use these equations, A is always equal to G. Now, Pizzuto, is that going to be negative 9.8? Yes, for Earth. We're not going to use 10 when we do this math. When we do these equations, we'll always use negative 9.8. I want to be clear about that. We were using negative 10 when we were talking concepts, but now that we're moving into the equations themselves, we will use negative 9.8. So A is always negative 9.8 when you're on Earth. Now, if you're on another planet, it's going to be that other gravity. So if it doesn't say what planet you're on, it is a fair assumption to assume that you are on Earth. So let's break this down. We know a ball is thrown vertically 28 meters per second. So this is 28. So I know this is 28, okay? What's the speed that's going to come back at? Pizzuto, it's not asking. I know, it's not asking for that. It's going to come back at negative 28. Let's just start thinking concepts. Every time we look at a situation, if we start just labeling things that we know, we can start identifying the parameters of the problem and start figuring out what goes where a little bit better. I want the t total. That's what this problem's looking for. All right? But what do I know? Well, it's giving me the V0. The V0 equals positive 28. All right? We always, if we are doing a vertical throwing problem, if you know the V0 and the A, they never change. They are always the same. They are always the same. So there are actually 2 correct ways to solve this problem. There is the way that we go over most frequently in class, where we recognize that at the top of the path, the velocity is 0. And I said that every time, and that would correspond to a time of t up. This is t up. So if I used a velocity of 0, I could then use an equation to solve for t up. This is legit. This will always give you the right answer. So if you like this way, that's great. You should use it. We're looking for t up. 0 equals 28 plus negative 9.8 t. Now, it doesn't matter if you label this t up in the equation, honestly. All that matters is you understand what you're solving for at the end. So this would be negative 28 equals negative 9.8 t. Divide by negative 9.8. Okay, so I got a t up of, let's say 2.86. I'm rounding. 2.86 seconds. I got a t down. Wait, I didn't solve for t down, but I know the rules of vertical throwing. I know that if I know t up, I know t down. 2.86 seconds. And I could just add those up and get t total. 2.86 plus 2.86 equals 5.72. This is legit. You got the t total. There is nothing wrong with doing it this way. You will always get it right if you do it that way. I just want to show you another way because, it's kind of what I want to do. I told you that the V0 and the A will stay the same. So I'm going to bring those two pieces of information here. But could I solve for t total directly? Okay, well, let's go back to this picture. T total corresponds to the time it takes to go from here all the way down to here. Oh, I know the final velocity. The final velocity is negative 28. Remember, each time corresponds to a specific velocity. So t up corresponds to 0. T total is going to correspond to negative 28. Oh, does this work? Let's see. V equals V0 plus AT. Negative 28 equals 28 plus negative 9.8 t. Curses, I am out of space. Minus 28 from both sides. I'm just going to move this up here. Sorry about that. I'm going to move it up here. But because you had negative 28 and you minus 28, this is actually negative 56 equals negative 9.8. And I'll give you two guesses as to what this is going to equal. But I think you only need one. I just want you to understand the interconnectedness of it all, and that there might be more than one correct way to solve an answer. Find the way that works for you and use it. So now, we have the exact same initial velocity. We have the exact same initial velocity. We know that we have the same acceleration. So again, we're just kind of building off of, each problem is kind of building off of each other a little bit more. Okay. We know that the T up is, what was it? It was, right, 2.86, thank you. Just from the other slide. Okay. So let's go back to the picture. I understand what this picture looks like. throw the ball up, comes back down, all right, up and down. If I throw this 28 and it takes 2.8 seconds to get up to here, where the velocity is 0, oh, interesting. I want the distance to find how high, the total distance traveled. I need to find out how high in the air it goes. I need to find the distance from here to here. Wait, Bizzuto. Wait. If I need the total distance, could I just take the t total, which I already solved from the other page, and it was the 5.72. Could I just take this and plug it into the d equation, the d equals v naught t plus 1/2 at squared? Please don't forget. Please don't forget. If you did that, that equation would equal 0. Because at the total time, that d solves for displacement. And at the total time, the ball is in the same spot it started. So the displacement would be 0. In all circumstances of vertical throwing, the displacement equals 0 when it's caught back in the hand. So to find the total distance, you have to find the highest height and then double it, because it's going to go up that height and it's going to come down that height. That's how you find the total distance. You found how high in the air it goes, and then you double it. Okay, that's not too bad. So how do I find how high in the air it goes? Well, you could use the d equals v naught t plus 1/2 at squared equation, but you can't use t total. You must use t up. You must use the time that corresponds from going here to here to the highest point. So you really need to think about your values and why you're using which one. And if you use a wrong value and you get a number like 0, you need to think about, well, why did I get 0? What am I conceptually saying is happening here? Sorry, out of space. I'm just going to do that. And I could just type this in my calculator. You can't see. I was just waving the calculator at the screen because, you know, that's what I do in my life. I hope you wouldn't mind, but essentially, it's 39.9999. I'm just going to call it 40. Okay? Questions about that? So it goes up 40 meters. It's going to come down 40 meters because if it goes up 40, it comes down 40. So the total distance traveled is going to be 80 meters. So I keep drawing this picture so you can conceptually understand why I'm doing the things that I am. 40 plus 40 is 80. Okay. Is there another way I could have gotten that 40? There is. You could have, if you wanted to, used the third equation, the one I really like. I like this equation. And the reason I like this equation is because I don't have to pick which time to use because there's no time in it. But the Bizzuto, what v do you use? Well, what v corresponds to the top of the path? Always. Oh, 0. 0 squared equals 28 squared plus 2 negative 9.8 d. I'm going to minus 28 squared from both sides. So it's going to be negative 784 equals, I minus that from both sides, negative 19.6 d. I'll give you one guess what that equals. I like this equation more. But it doesn't matter. Both equations give you the same answer. It doesn't matter. It doesn't matter. Pick the one that works for you. A ball is thrown vertically 28 meters per second. How can you find when it's going the fastest and the slowest? I think this question tripped a lot of people up because they wanted to go ahead and make it harder than it was. And this goes back to understanding the concept. We understand in vertical throwing, it's going the fastest at the bottom, and it's going the slowest at the top. Specifically, the slowest speed is always going to be 0, and the fastest speed is always going to be the initial velocity. These are always the slowest and fastest speeds of vertical throwing. So, when is it going slowest? That's going to be T up. The time it takes to get to the top is when it's going the slowest, because when it's going 0, it's going the slowest. And we know that the T up is the time that it takes to get up there. In our case, it was 2.86. We already solved for it. So you can give me exact numbers. When's it going the fastest? 0 seconds. But it's symmetric. What's the other point? T total. The very beginning and the very end. That's when it's going the fastest. A ball is thrown vertically plus 28 meters per second. How fast is it going at 1.8 seconds? At a question like this, I don't even need to draw anything. It says how fast, so I'm looking for a v. And it gives me a time of 1.8 seconds. I told you that every velocity has a time that corresponds to it, and vice versa. So we're not going to use a t up here. We're not going to use a t down. We're not going to assume the velocity is 0. We're going to solve for a unique set of velocity and time. We always know that our v0 never changes. I'm keeping it the same for simplicity. And then the a is negative 9.8. We can just plug it right into this equation and keep it moving. When I type that jump in my calculator, I get a velocity of, hold on, I remember that T up was 2.86. So at 1.8 seconds, should this still be going up or should it be coming down? Remember, so what this means is from 0 to 2.86 seconds, it's going up. And from 2.86 to the total time of 5.72, it's going down. Remember, that's the range of times. Half the time is up and half the time is down. 1.8 falls in this first range. It's between 0 and 2.86. So my answer had better be positive because it's still going up. And when I type it in the calculator, it is. These are little things that you can ask yourself to kind of check your work. It's like, oh, I expected a positive answer, but I got a negative one. What went wrong? Or vice versa. These are how you can check your work. Because some people have been saying in physics, I get numbers and I have no idea if it's right. These are the questions you can start asking yourself to kind of check your work. The same logic is going to apply here. A ball is thrown vertically 28. So we have our v0 is positive 28. Our a is negative 9.8. Okay, we know that. We know that. That's the constant. Okay, awesome. So if we're looking for a time, with this velocity of negative 12. And again, it's not going to be t up, it's not going to be t down, it's going to be a unique time. Every velocity has a unique time that goes with it, and vice versa. But I know a range of numbers. I know that t up is 2.86. So remember, I just said from 0 to 2.86 seconds, it's going up. From 2.86 to 5.72, it's going down. So because it's negative, my answer had better be in this range of numbers. This is just a way of checking your work. You don't always have to do this. I'm just trying to show you ways to think about and connect your answers to everything else in the problem. V equals V naught plus AT. Negative 12 equals 28 plus negative 9.8 T. Negative 28, negative 28. And you best believe that falls in the range of expected answers. 4.08 is in between 2.86 and 5.72. Nice. Okay. Here's one little twist. I'm switching it up. We're leaving the 28 meters per second initial velocity. And now it says a ball is thrown. It's in the air for 13.3 seconds total. Let's look at this. Picture time. Basuto, you and your pictures. I know. So what I'm saying is it takes 13.3 seconds to do all of that. That's the T total. If I know that the T total is 13.3 seconds, I know the first rule of vertical throwing. It says half the time is up and half the time is down. That's what the first rule of vertical throwing said. I don't know why I need to do the hand gestures. I'm not recording myself. But half the time is up and half the time is down. So 6.65 seconds up and 6.65 seconds down. Half. You just divide it by 2. Oh, great. Pizzuto, we didn't get the initial velocity yet. I know, just watch. But we just saw for the T up, which corresponds to the time it takes to do that. And we're looking for the speed here, and we know the speed here. We always know the speed here. That's the second rule of vertical throwing. Okay, so you're saying if I use T up, I know that the velocity is 0. I'm looking for the V naught. And, oh, right, always no gravity. Always no gravity. So you can just use this equation, and you can solve for V naught. So 0 equals V naught plus negative 65.17. Add that to both sides. There you go. You got your V naught. And now that you have that, you can do a lot. Once you have the V naught, you can get the distance up. You can get the distance down. You can get the total distance traveled. You can get the total distance, total displacement. Total displacement is always going to be 0. With the initial velocity, you can look at the times and you can figure things out like, oh, how fast would it be going at, 4 seconds now? At what time would it be going negative 12 meters per second? I know we just did that, but like with the initial velocity, you can then use this in all the other equations to solve for the other things as well. So once you have the initial velocity, the acceleration, and the times, you've really unlocked everything you need to solve for the other stuff in a problem. Wait, so vertical throwing charts. Didn't you say that you made a video on vertical throwing charts already? I did. I absolutely did. But I want to show you a couple of things. A couple of little neat tricks that we did go over in class. It doesn't say we're not on Earth, so we're going to assume that the gravity is negative 9.8. So that means every second that happens, the velocity changes by negative 9.8. So I have 3.4, I'm just going to minus 9.8. And I'm just going to keep minusing 9.8. Minus 9.8. Okay, that's all I'm doing. I'm just minusing 9.8. Okay. Okay. Oh, no, that's a 6. Thank you. And then to go up, I can just add 9.8 because when you go in the opposite direction that we saw before, you'd use the opposite sign. This is 13.2 meters per second. Okay. And what you could do if you wanted to was you could just keep building this chart up and keep adding 9.8 until you got to 0. Remember, all charts start at 0. You could do that. I just want to show you another way. They gave you this information. We know that the acceleration is 9.8. And they're saying that at time 6, the velocity is 3.4. Could I use all that information just to solve for V0 with an equation? Sure thing. V equals V0 plus AT. The V is 3.4 equals V0 plus negative 9.8 times 6. Negative 9.8 times 6 is, of course, negative 58.8. I'm just out of space. Shoot. Put it up here. Equals V0 minus 58.8. Doesn't matter. I'm just going to add it to both sides. To both sides. (62.2 meters per second is the V0. And once you have the V0, the rest of the chart unlocks pretty quickly. Wait, Bizzuto, could I have done that with any of these? Yes. It wouldn't matter which one you picked. If you plugged into that equation, you would always get the same V0. So there are so many ways here to get the initial velocity. And once you have the initial velocity, then you can calculate the time up. I can look at this chart and I can tell you that I know that the time up is going to be between 6 and 7 seconds because that's when it transitions between positive and negative. But I can't tell you the exact decimal yet. I would have to calculate that. And you know how to do that now. And once you get the initial velocity, you can easily solve for the displacement using this equation, d equals v naught t plus 1/2 at squared. There's a plus. That's a plus, not a big T. And if you don't remember how to use that equation, go check out the other video. Okay, Bizzuto, you said that. That's fine. That's great. But what if you're on another planet? What if you're on another planet? How the heck am I supposed to get all this information now? Because I know that I'm on another planet, so gravity is not Negative 9.8. It's got to be something else. Gravity is not negative 9.8. Well, gravity is an acceleration. And acceleration is a change in velocity over time. Remember these old equations? Maybe if I wrote this exact same chart like this, you might feel a little bit more comfortable solving it out. 25.5, 4, 5, 6 is 12. If I said, hey, what's the acceleration of this chart? Bet you could all get that. This is the exact same chart, it's just flipped. Don't let it mess you up. It's the same concept. You're going to subtract the velocities. You always do final minus initial. You always do the one more right minus the one more left. And you divide it by the number of seconds that it takes to go from 3 to 6. 1, 2, 3. 3 jumps. 6 minus 3 is 3, essentially. What is 12 minus 25.5 divided by 3? That's it. There's the acceleration. And once you have the acceleration, you can fill in all these blanks, because 25.5 plus negative 4.5 is 21, of course. Of course. Plus negative 4.5, 16.5, 12, 7.5. If I wanted to, I could use any of these pairs of numbers. I could use 4 seconds at 21 meters per second to solve for the V0, or I could just count back on the chart. But if you count back on the chart, I must warn you, you have to go all the way to 0. The biggest mistake that students make with the counting back of the chart is they don't go all the way back to 0. 30, 34.5, 39 is your initial velocity. Remember, V0 really means the velocity at time 0. So you have to go all the way back. And you could then solve the displacements, no issue. When you use this equation, d equals V0t, the V0 would be the 39. And don't forget, the A isn't 9.8 anymore. The A had better be your new gravity. Okay, so we're getting there, but there's just a few more things I'd want to address. Okay, now you have these questions that are just this. There's nothing else to ask. It says you're on Earth and you throw a ball up 17 meters per second. Okay. I like my picture, it helps me. I want to know how high in the air does it go. Okay, all right. So I'm going to label it now. I know this is plus 17. I know it's going to come back negative 17. I know that the velocity at the top of the path is 0. Okay. How high? Looking for the distance. I'm looking for the distance that corresponds right here. Oh, this is what I would do. You could solve for t up if you wanted to. You can. You'll get it right if you do that. But I really want to push the third equation. Once you know the V0 and the A, they're the same, always. I want to push my equation that I like. I'm going to push it one more time. Maybe you can see the value in it, because now you don't have to solve for a t up. You could solve for t up, and then use the t up in the d equals V0t plus 1/2 at squared equation. Go ahead and try that on your own. I'm not going to show you that way here. But you can check your answer, because your answer will be the same. Okay, so let's see this. Of course, 17 squared is 289. 2 times negative 9.8 is negative 19.6. D minus 289 minus 289. So negative 289 equals negative 19.6. And I'm going to get 14.74 meters is the distance. And that corresponds to the distance where it goes from 17 meters per second to 0. So it corresponds to the height. Remember, the total distance traveled would be that times 2, and the displacement would be 0. Remember how all this connects. You are on Earth and you throw a ball straight up and it's in the air for 4.6 seconds total. How high in the air did it go? Okay, it's a similar question, but you're starting off with a different piece of information. Let's see if we can break this down. It goes up and it comes down. T total is 4.6. Of course. Okay, so if I know that, right? Oh, I know that T up is half of that. And T down is going to be the same thing. Unfortunately, this time I do need to get the V naught. I do need to get the V naught. So my V naught is something I'm going to have to solve for. I know my A is negative 9.8. And we know that the top of the path of V is 0. So let's do this. I think we're old hands at this now. V equals V naught plus AT. 0 equals V naught plus negative 9.8. And of course, we've got to use T up. T up corresponds to a V of 0. 2.3. Negative 9.8 times 2.3. I'm skipping some algebra because I think you get it now. 22.54. The reason I'm skipping the algebra is because I want to get right to the equation. So I did the equation I like last time. You can do that again. Or you could go ahead and use the D equals V naught T plus 1/2 AT squared. I'm going to show you this way this time. D equals the V naught is 22.54. The time is 2.3. You've got to use the T up because that corresponds to the highest point. Don't forget those little details. They will mess you up. 1.8 times 2.3 squared. You simply just type all of this in your calculator. And you should get about 25.9. That's it. Don't let these things intimidate you. Even if you had something like this. Even if you had something like this. Now you're on another planet. You're on another planet, unknown gravity. Unknown gravity means A is not negative 9.8. It's something else. I'm going to draw my picture because my picture helps me. I throw the ball plus 15. Even if gravity is not negative 9.8, vertical throwing still works the same. It's coming back negative 15. And it returns to my hand in exactly 6 seconds. If I know that, then that's 3 seconds up and 3 seconds down. And I know that the velocity at the top of the path is 0. That's always true. That doesn't depend on Earth's gravity. That's any vertical throwing. So, I know the V naught is 15, positive. I know that the T up is 3, half the time is up. I know the V is 0. Remember, T up and V always correspond, and a V of 0 always correspond. I'm looking for the A. Let's do it. V equals V naught plus AT. 0 equals 15 plus A times 3. A equals -5. What you have in front of you is a list of tools. And if you conceptually understand how vertical throwing works, you can use your tools correctly. Take some time and try to visualize each problem. Understand what you have, understand what you're looking for, understand what you know, and you should always be able to solve the problems well. Good luck.